We've already looked at electrical resistance, and in this video we're going to look at a related quantity called the resistivity. Jumping right into things, here's the equation that relates resistance, which is R, to the resistivity. If you remember back maybe in your chemistry class when they talked about intensive versus extensive properties, an intensive property is something that just depends on the material but doesn't depend on the extent or how much of the material you have. So the resistivity is the intensive property, and the resistance is the extensive, where it depends on how much of the material and its shape and all of these things. So the resistivity, this Greek letter rho here, it's kind of like the resistance per unit length, but it's actually the resistance times unit length. If you look at the units over here, it's ohms times meters. And that's because it's not only dependent on the length of the wire, but also the cross-sectional area of the wire. So cross-section. Having a hard time writing. Here we go. So as we get a longer wire, we get more resistance, but as we get a larger diameter wire, we get a smaller resistance. And what good is an equation without a fun little applet to look at it, in case you don't understand basic algebra? As we change the resistivity, and we change that by changing the material, like copper has a different resistivity than gold, well then that obviously changes the amount of resistance in the wire. What this animation is showing here is some materials with higher resistivity. It's like they have more particles impeding the flow, right? Okay, if we have a longer wire, that also increases the resistance. Pretty cool animation. If we have a larger wire, that actually decreases the resistance, basically because there's more paths for the current to flow through if you have a larger area versus trying to force that current through a really small tube in this case. Alright, back to the presentation. So on the table here we have resistivities for a number of different materials, including alloys and whatnot. So a lot of times you'll have to look these up in your book. If you don't have your book with you, you can ask me, and if I'm in a good mood I might tell it to you. Alright, the other property we're going to look at over here, this is the same resistivity, but the resistivity of certain materials changes with temperature, and that's what this equation here is all about. So you take the resistivity that you know at a given temperature, that's kind of your reference point, and then you can find the resistivity at a different temperature, another temperature T, and then it scales by this factor of alpha here. So different materials, not only do they have different resistivities, but their resistivities change at different rates depending on the temperature. And you'll notice something interesting here. These guys all have negative resistivity temperature coefficients, the semiconductors. Typically it's good that they have positive temperature coefficients because that gives it kind of a feedback loop that works in our favor. If you have some copper wires and you're running current through them, then they're going to get a little warmer, just like running current through a toaster wire gets hot. And when it heats up, that's going to increase the resistance, which will decrease the current so it doesn't overheat. If it were the opposite, as it heated up, the resistance went down by V equals I times R. If the resistance goes down, then the current's going to go up, and that's going to cause it to get even hotter, and so you'll have a runaway circuit until things start melting. So we have to be careful with our semiconductors, but this is a useful property if we control it right in the right situations. Alright, let's just do a couple of quick examples and then we'll call it good. If we want to hook up some speakers and we want to make sure that we have less than 10 ohms of resistance per wire so that we get the optimal sound quality or whatever, we can use our resistivity equation, which was the resistance equals resistivity times length over area, and we want to find what diameter of wire we should use. So if we're selecting our speaker wire or something, we might want to look at this, and that will tell us what gauge wire we need. So we just plug in 0.1 for the resistance. The resistivity of copper, we're going to have to jump back and grab that. 1.68 times 10 to the negative 8th. 1.68, 10 negative 8. The length, they have to be 20 meters long because that's how far away our speakers are or whatever. And then we can use this to solve for A. A turns out to be 3.36 times 10 to the negative 6th. But that wasn't exactly what we were trying to find, right? We want diameter. So we can relate this to the radius through pi r squared. If we solve that for r, we get 0.00103. There's an O in there. And this is going to be in meters because I did everything in standard units. So the diameter is going to be double that, and then if we go ahead and round that up a little bit, we get 2.1 millimeter diameter for our wire. Alright, second part, if the current is 4 amps, what is the potential difference, aka voltage, across each wire? This is pretty straightforward. V equals I times R. We've got our current, and then we multiply that by the resistance, which was 0.1, so we get 0.4 volts. And this is typical. The voltage on speaker wires is typically very low. Kind of a conceptual example here. If we have a wire of a given resistance, I'll call that R naught actually, and then we stretch it uniformly until it's twice its length. So if we imagine we heat it up a little or something so it's more soft and we stretch it out, well, the amount of material is constant, so we're going to say that the volume is constant, and the volume of our wire is the area, the cross-sectional area, times the length of the wire. So if we double the length, in order to keep the volume constant, we have to divide the area by 2. So that's what we do, and we get constant volume. And then if we look at what happens to our resistance, well, that's resistivity over times L over A. And if I say this is my initial, then my final is going to be that same resistivity times twice the length times A over 2, which that ends up multiplying up top, so you end up with a factor of 4 times your original resistance. Alright, last one, we're going to look at temperature change. So you can read through there. Yes, you can make thermometers by measuring resistance. Essentially, we've got platinum wire, wonderful metal, at 20 degrees Celsius, and this is the resistance. If the resistance changes to this value, what is the temperature? So our equation was resistivity equals some reference resistivity times 1 plus the temperature coefficient times the difference in temperature. By the way, this has to be done in Celsius or kelvins. You could do either because it's a difference, so you'll get the same thing, but do not use Fahrenheit, please. Now, here it gives us resistance values, and our equation is in resistivity values, but all we have to do is multiply both sides of our equation by L over A, which is a valid thing to do, and these resistivities become resistances. So, goodbye resistivities, hello resistances. So you can use either way, either of those quantities for this equation. So now we just go ahead and plug in some numbers. The final resistance was 187.4, the initial resistance 164.2, 1 plus alpha, you have to go look it up on the table, but I wrote it down earlier, so here we go. This is alpha for platinum. The final temperature is what we're going to find, and we've got negative 20 degrees Celsius. I will spare you the algebra. I'm sure you guys can do this. You end up with a final temperature of 55.98 degrees Celsius. And that is all. Have a good one.